coming out. Coke. All right, Coke. No drink Coke? What's your favorite beverage? Whiskey? Good answer. Good stuff. Oh, better stuff. Irish whiskey? Sure. Oh, good answer. All right, so SO3, so then the next one would be the SO3H sitting up there. Or down there would be just fine. Okay? All right, I'm yours. Yeah, the 4 position would be different. Now, they did this specifically because, let's go back to what we did over here, just for a minute. Remember when we came in here, and if we took a BR and a BR, you know, well, let's do the HBr, that's going to be a little bit HBr. We came into here and kicked that out and added that right there, correct? And we use these as our Lewis base, and that's what that 383 page is talking about. So if I come over here, this is my Lewis base, right? So if he donates into here, that's going to push these electrons out and onto here. Oh my gosh, that's where that bromine landed. See, you could actually predict that just by doing that. And that's what makes all this easy. I believe that the biggest fallacy of this book is to give you the Bronsted acid definition in 1110 instead of the Lewis-based Lewis acid definition. Because if you come in here with Lewis-based Lewis acid, you could really just push those electrons and get it right off the bat, because that's really the same thing. Yeah. And of course, you might say, well, how did it work up top? Well, these electrons are free to move around. This is still the same compound, so then I would come and push it up to here, and it would go up to there also. So those shows you the 2 places it would go. And I'm sure Ezra in his mind probably just does that, which is good. But all right, next.
One question before you erase it. Sorry.
Okay.
So there's 2 electrons that come off the top of the oxygen.
Mm-hmm.
How do they get replaced? What happens to that?
So what happens when it comes down in? If you look at this whole mechanism, this comes in and comes out and picks up the bromine. Okay. So that means then the next structure I would draw, because what these arrows mean is that I'm forming a bond here, would be a bond right here. So I would have this bromine here, a bond right here to this methyl, and this would have a plus charge, just like a hydronium. Remember the hydronium ion, anytime oxygen had 3 bonds, it had a plus charge, 1, 2, 3, it has a plus charge. And so right here, this not drawn in, are the hydrogens. So what happens now is in here you have what's left over. This was Br2 plus FeBr3, right? All right. So what happens here is iron sits clear down here. Iron is somewhere here in the metals, right? So iron conducts electricity. Iron is attracted to negative charges. So in the beginning, and this is what we have drawn, if you go back to that PowerPoint slide on it that we just ignored, this is all laid out in case somebody's interested. So you've got the Br and the Br, and it attacks the iron. This is the Br3, the Brs are just out here. So this comes in here and attacks here, and that's what allows this to be picked up. Okay? So when it's over, you have this FeBr3 that's a minus charge. It picks up this hydrogen, and so these electrons collapse down in and go right back up to quench that charge. And that happens on all of them. So that's a lot more complicated than what we would do, but it is understandable in that pushing electrons kind of thing. Yes?
Maybe a silly question, but on the hydronium, if the oxygen still has that extra room here, why would it be a positive?
So in terms of looking at a molecule, what you have here is an oxygen that has, we're going to go back to 1110. This is the other thing. In 1110, because you kind of memorize these things, it really doesn't give you what their implications are. So, 1, 2, 3, 4, 5, 6. So how many protons are in this nucleus? 6. Okay. And because this brings 1, 2, 3, 4, 5, 6, how many electrons will this have? Okay. So it has 6 electrons, right? So we're going to talk about you and your neighbors. So if I'm right here and I have an oxygen, I bring 6 electrons to the table. I own these outright. They're my lone pair. That's my Lewis base. I own both of them. But I've shared some others. Okay? So I've shared 1, 2, 3, 4, 5. If I bring 6 and I've only really owned 5, that equals a +1. That means that I had to donate these electrons, 2 of them, to something else. Does that make sense? So what really happened is, in water, there was a proton. And so I donated 2 of these. And by donating 2 of these, I end up here at the hydronium, and it means that I need 6 to balance the 6 plus charges in here, but I only have 1, 2, 3, 4, 5, because I actually donated another one. I gave all of my money away, and now I don't have enough money to exist. So this is showing you that this thing needs a pair of electrons. I think you guys probably drew the hydronium like this, or something, right? Instead of organic or medicinal chemists, we need to know where that charge is. It's on the oxygen. So what that tells you is, while oxygen is almost the second most electronegative element here, what do you think it would be if you put a plus charge on it? Think of it in terms of money. If I had so much money, but I had a neighbor that was needing, and I went and bought them groceries too, and that left me with less money, I would be trying to collect more money, right? So that means this oxygen right here, with the plus charge on it, is more electronegative than anything on that table. And because it's more electronegative, it's pulling electron density away from all of these hydrogens to help balance this plus charge. And that's why these are barely hanging on. And that's why these are your acids, right? Because an acid is just an H+. And so if something came in like a base, there's my lone pair. It would pick that up and kick that out, and that would quench the charge, and it would make water perfectly happy, and then I'd have 2 waters. And that's that ion exchange you talked about in 1110. So that's why we draw it with that plus charge right there, because it shows who needs the electrons and where they're pushing and pulling. So that's, and so this guy would come in and pick that up, and this would come back onto there and quench that out. And none of that is on the test. I'm just happy to answer all your questions. Wow, next question. Yes?
Okay, so for that, never mind actually.
I'll draw it.
Oh, okay, so basically with the, with the shape of it, couldn't you add it onto the other side? So like you had it, the methyl going off the top
Is that
middle?
this guy right here?
No, I think it was,
Methyls?
I think it was like C, like the SHO, right? Yeah.
Oh, it had the 2 on this side. Okay.
Right?
Yeah,
That
but
should
weren't
be
they
it.
like, they were like SO instead of the.
The SO, so this guy right here that we put on it, SO3H,
Yeah, couldn't you put it to the one to the left of the top
you
middle?
put it to this guy right here.
That would be the same though, right?
Yes.
But then
But
you
over
just-
here, it would be different.
Are you, so if you had 2 answers for it, could you draw both of those? Or is it?
So here's, if you had 2 answers, this would be the same. You could draw it over here, but that would be a minor product, and I don't know that your book would actually give you that. And the reason that this is the way it is that this donates electrons into here, and that makes this side better. So this is the side that would pick it up on either side there. That's beyond the book. So again, this is the problem with that. With that problem, you're not given anything to tell you where it should go. So at that point, if you drew it over here, yeah, I'll give you credit for it. Even though that's the minor product, I know that your book has given you no tools other than to memorize something inside there to do that. So yeah, you can relax a little bit in that. I'm keenly aware of what is and is not in the book. So, but that's a good point. Yes, I would have given you full points for that, but then looked in the book and given you, this is where your book shows it, and this is why. You know, so you understand why. But yeah, you got points for that. Yes.
So there was a slide in the notes, kind of by where we were learning how to name all those special benzene rings.
Mm-hmm.
But there was one that was 3-methyl-3-phenylpentane.
Okay, so let's go pentane.
Well,
1, 2, 3, 4,
No, so
5.
it was like a benzene ring.
3-methyl, that's going to be a CH3, and 3-phenyl is going to be a benzene ring. When phenyl, so like when methane is connected to a ring, another group, it's a methyl. When benzene is connected to another group, it's a phenyl.
But why are we naming it based off the pentane if it doesn't have more than 6?
Ah, good point. So going back to those rules of the cycloalkanes and even benzene, the rule stops at if you have more carbons on the chain than you have on the ring, then the ring becomes a substituent, right? And then if you have more carbons in the ring than you do in the chain, then the ring becomes a substituent. And so at that point in class I said, so, okay, so what's missing here? What happens when they're the same? And then those 5 rules of nomenclature that we talked about come into play. And that is the rule that says if you have a choice, you go to the one with the most branch points, you know, as your main chain. And so here, and what that really means is to go to the most complex. We want the parent carbon to be that is the most complex. So this has only one group off of it, right? But this has 2 groups off of it. Which one's more complex? The chain. So that's why this is a 1, 2, 3-phenyl, 3-methyl pentane. Because you went through the longest chain that bears the most substituents on it.
Okay.
Now, if you would have named this using this, it would still be all right. It's just that your book didn't give you any tools to do it. But here's how this would be. This would be carbon number 1, okay, off of here. So we would use the rule 5 nomenclature. So rule 5 would say that I either go 1, 2, 3 or 1, 2, 3, and it doesn't matter. This would be then, if we just list it this way for simplicity, 1, 2, 3. If I'm going to use rule 5, this would be then a 1-ethyl, 1-methyl-propyl benzene. Remember rule 5 says you start at the point of attachment and you give that carbon number 1, and then you go out to the longest chain. You got 3 here and 3 here. So at position 1 is a 1-ethyl and a 1-methyl, and the overall longest chain is a propyl, and so that would be a 1-ethyl, 1-methyl-propyl benzene, and you still could name it correctly that way.
So I guess I'm just confused why they're using the chain, like, because they don't have the same amount of carbons. The chain has less carbons than the ring. So why is it going to the most complex if they don't have the same amount?
Mainly, it's practicing that rule too that says, okay, start at the end, here's the first branch point, and if you have a branch point that is equidistant on the other side, then you go to the one with the next branch point, or if you get in the rules, it'll say you got a 7 chain here and a 7 chain here. Which one of the 7 chains should we use? The one with the most substituents on it. You remember that?
So that makes sense to me if like it were hexane, not pentane.
Okay, I'm going to get to that.
Okay.
So what it's telling you is you really name the most complex portion as the parent chain. So if you go into those rules of the cycloalkanes, you will see examples of that where it's actually the chain now that is more complex, even though it's less. And to illustrate that, we went like this in the class. Because when you get this as a major functional group, you start at that end, so this is actually a methanol, right? So it's a 1-phenyl-methanol. I'll just erase that because this is nonsense. So what that's telling you is that you're always going to the most complex. It's like chess. You know, it's the most substituents, the most people, the most, okay, chess is probably not that great an analogy. But because this is the most complex, that becomes the parent chain. So that's worth keeping in the back of your head, because as you get out of the alkanes, you're really going to focus on the parent carbon, regardless of how long it is going to contain that function group highest priority. Now, what if I have the function group in 2 different places? Then we would look for which one has the next most substituents. That would be the most complex. So in here, this was a problem in your book?
No, in the notes, like on the slide.
Okay, and so that's what I'm saying in terms of the reason I gave you the 5 rules of nomenclature is that you see that you'll get these in the challenge problems or something that your nomenclature didn't give you the tools to do that. And so it really is, this is the most complex point in here, so that's why. Now, that said, we lectured on it, but we're not going to give that to you. In other words, I see the fear of in some faces. I'm not going to do that to you right here and now. So this is your first look at nomenclature. Trust me, we're going to see nomenclature in every single chapter down the road for the organic section. When we get to the bio section, then it's a bunch of memorized names. But we will eventually get to that part, and then this will clear up in that the most complex component, regardless of its length, is going to be the major one.
So had that not had the little methyl, then you would just
Had that not had the methyl group, you're right, then this would have been, this has one group and that has just one appendage, so we would have named it here because a ring is more complex than an open chain. Okay. Any other questions? One more quick before we go? Yes?
So on that methanol that has like the benzene ring, there's another methanol on the other side. How can you build that?
Ah, well that would be painful, wouldn't it? We would never give you that, but if it was longer, okay, then this would be a 1, 2, 3, 4, it would be a, so this would be 1, 2, 3, this would be a 4-phenyl methanol group connected to your ethyl. Now, you'll never get that, but it's a good question. So, take home for today, much of this were your questions that are awesome because they're deep in thought.